blockchain, where we are going through the Flow blockchain's tutorials to help you learn how to use the Cadence programming language to build decentralized applications, otherwise known as dApps, on the Flow blockchain. If you missed the first lesson where we introduced Cadence and the Flow blockchain, go back and you can watch that to get a quick introduction on what the Flow blockchain is, what is Cadence, and how do smart contracts and transactions work in the Flow playground. In this lesson, we're going to be using the Hello World project to deploy our first smart contract onto the Flow blockchain. Let's get started. So for this lesson, we're going to write and deploy our first smart contract. If you would like the starter code, we can just quickly open up the Flow playground preloaded with the Hello World starter code, which is what we'll do. Open the starter code in the Flow playground. This tutorial will be asking you to take various actions to interact with the code. Instructions that require you to take actions are always included in a call-out box like this blue one. These highlighted actions are all that you need to do to get your code running, but reading the rest is necessary for understanding the language's design. A smart contract is a program that verifies and executes the performance of a contract without needing a trusted third party. Programs that run on blockchains are commonly referred to as smart contracts because they mediate important functionality, such as currency, without having to rely on a central authority like a bank. Before we get started with Flow, we'll need to understand how accounts and transactions are modeled. Accounts and transactions. Like most other blockchains, the programming model in Flow is centered around accounts and transactions. All persistent state is stored inside of accounts. The interfaces for this state, the ways to interact with it, are also stored inside of accounts. All code execution takes place within transactions, which are blocks of code that are submitted by external users to interact with a persistent state, which includes directly modifying account storage. Each user has an account controlled by one or more private keys. This means that support for accounts and wallets with multiple controllers is built into the protocol by default. An account is divided into two main areas. The first is a contract area. This is an area that stores any number of smart contracts that contain type definitions, fields, and functions that relate to a common functionality. This area also holds contract interfaces, which are basically program guidelines that other contracts can import and implement. This area cannot be directly read from in a transaction unless the transaction is just reading the code deployed to an account. The owner of an account can directly add, remove, and update or overwrite contracts that are stored in it. Second, the second area is the account file system. This area is where an account stores the objects that they own and the capabilities for controlling how these objects are accessed. Objects under paths in the account file system. Objects are stored under paths in the account file system. Paths consist of a domain and an identifier. Paths start with a character / followed by the domain, the path separator / and finally the identifier. For example, the path /storage / test has a domain storage and an identifier test. There are only 3 valid domains which represent the 3 areas in an account file system. They're storage, private, and public. Identifiers can be any name you want them to be to indicate what is stored in that path. The storage domain is where all objects such as structs and resource objects representing tokens and NFTs are stored. It is only directly accessible by the owner of the account. The private domain is like a private API. You can optionally store capabilities to any of your stored assets here. Only the owner and anyone they give access to can use these interfaces to call functions that are defined in your private assets. Users will commonly store private capabilities here that refer to other accounts' private objects. And finally, the public domain is kind of like your account's public API. The owner can link capabilities here that anyone else in the network can access to interact with the private assets that are stored on the account. So you've got a diagram here with the account at the top. Then you've got contract code underneath that account. Inside of the contract code beneath that, you've got a storage, which is where we actually hold resources, and then we can reference that storage using both our private and our public, private and public domains. 3 domains again are storage, private, and public. only the owner can access storage in private, and public can be accessed by anybody. A transaction in Flow is defined as an arbitrary arbitrary sized block of Cadence code that is signed by one or more accounts. Transactions have access to the storage and private domains of the account that signed the transaction and can read and write to these domains, as well as read and call functions in the public contracts and the public domains and other users' accounts. Okay, so that was a lot about accounts and transactions. Now let's get into creating a smart contract. We will start by writing a smart contract that contains a public function that returns hello world. First, you'll need to follow this link to open a playground session with the hello world transactions, contracts, and scripts preloaded. I believe I'm already here, ending with 93C. I'm already here, ending with 93C. I'm already there. Open the account 0x01 tab with the file called helloworld.cdc, which should contain the following code. I've opened up account 01, and then inside of that we should see the contract, the public contract of hello world. It should have a greeting, an init, and a hello function. We've got a greeting, an init, and a hello function. A contract is a collection of code, its functions, its data, which is its state, and that lives inside the contract of an area of an account in Flow. Accounts can have one or more contracts and or contract interfaces, and these can be freely added, removed, and updated with some restrictions by the owner of the account. The line pub let greeting string declares a public pub state constant let called greeting of type string. We would have used var if we wanted to declare a variable. The pub keyword is an example of an access control specification, meaning that it can be accessed in all scopes, but not written to in all scopes. You can also use access (all) interchangeably with pub if you prefer something more descriptive. Please refer to access control section of the language reference to learn more about the different levels of access control permitted in Cadence. The init section is called the Initializer. It is a function that is only run when the contract is created and never again. In this example, the initializer sets the greeting field to hello world. This is very simple, similar to a construction function or a constructor function in other programming languages such as Solidity. Next is the public function declaration that returns a value of type string. Anyone who imports this contract can read the public fields, use the public types, and call the public contract functions, i.e. the ones that have pub or access all specified. Now we can deploy this contract to our account and run a transaction that calls its function. Great, we have created the smart contract inside of our Flow playground. Now let's deploy this code to our local Flow blockchain. Now that we have some Cadence code to work with, we can deploy it to our account. Make sure that the account 0x01 tab is selected and that the helloworld.cdc file is in the editor. Click the deploy button to deploy the contents of the editor to account 0x01. We've got the contract highlighted. We have our 0x01 account selected. Let's deploy it. Boom, GraphQL access denied. Well, we got our access denied, which is no good. We don't like that. Let's see if the tutorial tells us anything about this. You should see a log in the output indicating that the deployment succeeded. Don't worry if the transaction number or block is different. I did not see a successful execution. I see access denied. So I wonder why we're getting access denied. I want 0x01. We're getting GraphQL error access denied. I wonder why we're getting access denied. Access is being denied here. I shouldn't be able to send anything. My access is being denied. I'm going to search this error to see why, because in the tutorial it doesn't talk about it. So I want to specifically include flow in the search as well as this error. No matches. Alright, I'm not seeing anything. Maybe I can save? What happens if I try to save? I think I was already here. I'm going to try deploying again and I'm going to get that same error. I'll select an account. Wonder why we're getting access denied. Documentation, Twitter, Discord. Alright, so it's not liking my access level. So there's probably something going on with authentication somewhere. I wonder if it's on Brave. I'm going to turn off my shields for Brave. Let's try deploying again with our shields down. Okay, so it looks like the issue is with my Brave shields. So if you're using the Brave browser and you're not deploying successfully, try turning off your Brave shields to see if it works. That was a good one. Let's keep moving on with the tutorial. So next up, we see a log deployed contract to 0x01. We successfully deployed the contract. Great. You'll also see the name of the contract show up in the selected account tab underneath the number of the account. This indicates that the Hello World contract has been deployed to the account. You can always look at this tab to verify which contracts are in which accounts, but there can only be one contract per account. So we can now see underneath our 0x01, we do have this Hello World contract that's been deployed. So everything's looking good, matching the tutorial so far. We've just deployed our code to the Flow playground. Now let's create a transaction that interacts with the smart contract that we just deployed. Open the transaction named Say Hello World, or Say Hello. And it should contain code. Open the transaction named. Well, I see a transaction named transaction, and I see one named script. I'm gonna try to start this tutorial again to see if I can see that, because I thought the last time I loaded this, we do have the Say Hello. So my Brave shields are off. I'm gonna quickly deploy the Hello World, and now we have this transaction template called Say Hello. And it should look something like this. We are importing the Hello World contract from our 0x01 account. We then declare a transaction with a prepare and then an execute. And the only thing that it's doing is logging hello world.hello. So I think we just want to send it. Let's send it and see what happens. We send the transactions and then we get hello world log. Ba-ba-ba. So we have successfully created a transaction on the blockchain using Cadence programming language inside of the Flow playground. This is a Cadence transaction. A transaction can contain arbitrary code that imports from other accounts, interact with account storage, interact with other accounts, and more. To interact with a smart contract, the transaction first needs to import that smart contract by retrieving its definition from the address where it is stored. This imports the interface definitions, resource definitions, and public functions from that contract so that the transaction can use them to interact with the contract itself or with other accounts that utilize that contract. To import a smart contract from another account, you type the line import contract name from address. So we can see that right here inside of this, we import the Hello World contract, the same contract name, from our contract address, same as our account address. Transactions are divided into two main phases, prepare and execute. The prepare phase is the only place that has access to the signing account's private auth account object. Auth account has special methods that allow saving to and loading from the storage and creating private and public links to the objects in storage, called capabilities, which will be covered later. The execute phase does not have access to auth account, and thus can only modify the objects that were removed in the prepare phase in call functions on external contracts and objects. By not allowing the execute phase to access account storage, we can statically verify which assets and areas of the signer's storage our given transaction can modify. Browser wallets and applications that submit transactions for users can use this to show that a transaction could alter, and users can have more confidence that they aren't getting fed a malicious or dangerous transaction via an application-generated transaction. You can have multiple signers of a transaction by clicking multiple account avatars in the playground, but the number of parameters of the prepare block of the transaction needs to be the same as the number of signers. If not, this will cause an error. In this transaction, we're importing the contract from the address it was deployed to and calling its hello function. In the box in the top right of the editor, select account 0x01 as the transaction signer. Click the send button to submit the transaction. We have already done this. We've selected our 0x01, and now I send the transaction, and then boom, again we get back hello world. Same as what they expect. Congrats! You just executed your first Cadence transaction. 100, but it didn't actually put the emoji, it just signaled that there was supposed to be an emoji. Next up, we just finished creating our first transaction. Now we're going to be creating a resource. Next up, we're going to get some practice with an example that uses resources, one of the defining features in Cadence. A resource is a composite type like a struct or a class, but with some special rules. We're now going to open the account 0x02 tab with the file named helloworldresource.cdc. helloworldresource.cdc should contain the following code. Let's see if it does. Open the account 0x02. Looks fairly similar. We've got a public contract called hello world. We've then got a resource called hello asset. And then we've got our init function. And we don't have any other functions. Looks similar. We've got the public resource of hello asset. And then we've got our init function. Let's scroll down and see what's happening here. Okay, they just want us to deploy the code to the account 0x02 using the deploy button. We'll deploy it and see if it's successful. We have deployed it. We got a successful contract deployed as 0x02, and we know that by checking the 0x02 account, and we can see that it has a hello world contract associated with it. This is another example of what we can do with a contract. Cadence can declare type definitions within deployed contracts. Any account can import these definitions and use them to interact with objects of those types. This contract declares a definition for the hello asset resource. Let's walk through this contract. We've got a resource hello asset with a public function hello, which returns a string. Very similar. You call the hello function, and then it returns the string. A transaction can call this function to get the hello world message from the resource. Resources are a composite type similar to a struct or a class because they can have any number of fields or functions within them. The difference is how code is allowed to interact with them. They're useful when you want to model direct ownership. Each instance of a resource exists in exactly one location and cannot be copied. They must be explicitly moved when accessed, making it difficult to lose accidentally. Structs from other conventional programming languages are not an ideal way to represent this ownership because they can be copied. This means a coding error can easily result in creating multiple copies of the same asset, which breaks the scarcity requirements needed for these assets to have real value. We have to consider loss and theft at the scale of a house, a car, or a bank account with millions of dollars, or a horse. Resources, in turn, solve this problem by making creation, destruction, and movement of assets explicit. Next, we've just talked about the first part of our contract hello world in account 0x02. Now we're going into the constructor function or the init function. This example also declares an init function. All composite types like contracts, resources, and structs can have an optional init function that only runs when the object is initially created. Cadence requires that all fields must be explicitly initialized, so if the object has fields, this function has to be used to initialize them. Contracts also have read and write access to the storage of the account that they are deployed to by using the built-in self.account object. This is an auth account object that gives them access to many different functions to interact with the private storage of the account. In this contract's init function, the contract uses the create keyword to create an instance of the hello asset type and saves it to a local variable. To create a new resource object, we use the create keyword followed by an invocation of the name of the resource with any init arguments. A resource can only be created in the scope that it is defined in. This prevents anyone from being able to create arbitrary amounts of resource objects that others have defined. So we assign to the let, which is a constant new hello, the creation of a hello asset. And we can see that inside of our init, we are creating a new variable called new hello, and we're assigning it to the creation of a new instance of the hello asset resource defined up here. So we use the hello asset, use some parentheses, and we create it to assign it to our variable. Here we use the less than minus symbol. This is a move operator. The move operator replaces the assignment operator equals in assignments that involves resources. To make assignment of resources explicit, the move operator less than minus must be used when the resource is the initial value of a constant or a variable, the resource is moved to a different variable in an assignment, the resource is moved to a function as an argument, or finally the resource is returned from a function. When a resource is moved, the old location is invalidated, and the object moves into the context of the new location. Regular assignments of resources are not allowed because assignments only copy the value. Resources can only exist in one location at a time, so movement must be explicitly shown in the code. Then it uses the authAccount.save function to store it in the account storage. Got self.account.save, the move of new hello to storage /hello. So we've got self.account.save less than minus the move operator, new hello to the path, storage with the resource of hello, the identifier of hello. We can do anything in the init function, including accessing the storage end of the account that this contract is deployed to. Here we're storing the newly created hello asset resource in the private account storage by specifying a custom path to the resource. So we take that new hello variable we just defined, we save it to the account at the path storage /hello. So we've now stored an asset or a resource inside of the private storage of the person who is deploying the smart contract. A contract can refer to its member functions and fields with the keyword self. All contracts have access to the storage of the account where they are deployed and can access that authAccount object with self.account. AuthAccount objects have many different methods that are used to interact with account storage. You can see the documentation for all of these in the storage section of the language reference or in the glossary. The save method saves an object to the account storage. This type of parameter for the object type is contained within less than greater than to indicate what type the stored object is. It can also be inferred from the argument's type. The first parameter is the object that's being stored, and the to parameter is the path that the object is being stored at. The path must be a storage path, i.e. only the domain storage is allowed as a to parameter. If there is already an object stored under the given path, the program aborts. Remember, the Cadence type system ensures that a resource can never be accidentally lost. When moving a resource to a field, into an array, into a dictionary, or into storage, there is the possibility that the location already contains a resource. Cadence forces the developer to handle the case of an existing resource so that it's not accidentally lost through an overwrite. This is also why we can't let the exception reach the end of the block without doing anything with new hello, and why save would fail if there's already a resource at the specified path. In this case, this is the first transaction we have run with the selected account, so we know that the storage spot of storage/hello is empty. In real applications, we would likely perform necessary checks and actions with the locations we're storing to make sure we don't abort the transaction because of an accidental overwrite. Now that we've stored a resource in an account, you should see the resource shows up in the resources box below the editor. The box indicates that the resources are stored in the selected account and the values of the fields inside those resources. Right now, you should see that the hello asset resource is stored in the account 0x02 storage and that it has no fields. There's a lot right there. Okay, we're inside of the 0x02 account. We're now looking for resources. Wonder how we see our resources. Let's redeploy. We don't want to redeploy. Okay, we should. I want to see our resources. I don't see a resource box below the editor. We're going to refresh and we're going to start over from scratch. Let's redeploy. Okay, we'll reset the state. But where is where are our resources? Right now I'm not seeing our resources. We've got transaction signers if we go down to transactions. We've got script templates. And we've got accounts. But I'm looking for our resources. Inside of the tutorial it says that there's a resources section underneath deployment result. Right now I'm not seeing it, and I don't want to spend a tremendous amount of time because this isn't critical, but I do like to follow the tutorial if it's possible to the T. I see contracts. Gonna redeploy the contract again. We're deploying the contract, but I'm not seeing anything for our resources. So we're just going to keep moving. Next section. We just talked about creating a resource. Now we're talking about interacting with a resource. Open the transaction named load hello. Load hello should contain the following code. We'll open the transaction load hello. Looks like we've got a transaction. Again, we're importing hello world. We're importing it from the account 0x02. We've got a transaction with a prepare, and the only thing it has is a prepare. We don't even have an execute. So we have the load transaction. The transaction imports the hello world definitions from the account we just deployed them to. It removes the hello world, the hello asset object from storage, and calls the hello function of the stored hello asset resource. To remove an object from storage, we use the load method. Let hello resource move operator account.load less than at hello world.hello asset from hello storage, and we can see that there's a less than, greater than, and then the path. Let's see where that is inside of our code. So here we say that let's read these comments. This transaction calls the hello method on the hello asset object that is stored in the account's storage by removing that object from storage, calling the method, and then putting it back in storage. So we first load the resource from storage, specifying the type to load it as, and the path where it's going to be stored. So we get hello resource, we do a move operator from loading something from our account, we get the hello asset from our hello storage, so we take it from our storage and we assign it to a variable. If no object is stored under the given path, the function returns nil. When the function returns, the storage no longer contains an object under the given path. The type parameter for the object type to load is contained inside of those brackets. That is the type parameter. A type argument for the parameter must be provided explicitly, which is at hello world.helloAsset. Note the at symbol to specify that it is a resource. The path from must be the storage path, i.e. only the domain /storage is allowed. Next, we call the hello function and log the output. So we take the hello resource and then log the output, and it looks conditional. We use optional chaining, similar to what we can use in JavaScript, because the value in storage may or may not exist and thus is considered optional. So up here we're trying to take something from our account storage and moving it to a variable. We're taking it out of our account storage, putting it into a resource, and then we're going to try to log the hello parameter from that hello asset resource, only if the resource exists, so conditional chaining. We use question mark because the values in the storage are returned as optionals. Optionals are values that can represent the absence of a value. Optionals have two cases. Either there is a value of the specified type, or there is nothing, nil. An optional type is declared using the question mark suffix. So we've got let new resource : hello asset question mark. It could either have a value of hello asset, or it could have a value of nil. Optionals allow developers to account for nil cases more gracefully. Here we explicitly have to account for the possibility that the hello resource object we got with load is nil. Using question mark unwraps the optional before calling hello, but only if the value isn't nil. If the value is nil, it returns nil. Because question mark is used when calling the hello function, the function call only happens if the stored value is not nil. In this case, the result of the hello function will be returned as an optional. However, if the stored value was nil, the function call would not occur and the result is nil. Next, we use the save again to put the object back in storage in the same spot. Very simple. We take the account and then we save. We move our hello resource to the path of storage /hello. So going through this whole prepare, we first we load an object from our storage and assign it to a variable. So our storage is now empty and we have a local variable that is assigned that storage value. We then log conditionally the value of our hello function with our local variable that we have taken from our storage. After we load it and we're done using it, we then put the resource back in storage at the exact same spot, and we use the force unwrap operator ! To get the same value out of the optional. It aborts if the optional is nil. So remember that hello resource is still an optional, so we have to handle the possibility that it's nil. Here we're going to use the force unwrap operator ! This operator gets the value in the optional if it contains a value, and aborts the entire transaction if the object is nil. It's a more risky way of dealing with optionals, but if your program is ever in a state where a value being nil would defeat the purpose of the whole transaction, then the force unwrap operator is a good choice to deal with that. Refer to optionals in Cadence to learn more about optionals and how they're used. We're now going to select the account 0x02 as the only signer, and then we're going to click the send button to submit the transaction. And we should see something like this, where we log hello world. So we're going to go down to the 0x02. We should have our transaction and now we're going to load it with 0x02, and now we'll send it, and we get back hello world, and we loaded it. So we launched this transaction. We took a resource from storage, assigned it to a local variable. We then conditionally logged the hello function from that resource, if it exists. And after we log that function call, we then save the resource back to the account's storage. And we got the value just like we expected inside of the tutorial. We just figured out how to interact with a resource. We're now moving on to creating capabilities and references to stored resources. In this example, we create a link and reference to your hello asset resource object. Then we use that reference to call the hello function. A detailed explanation of what is happening in this transaction is below the transaction code, so if you feel lost, just keep reading. Open the transaction name create link. Create link should contain the following code. Let's open up the create link, and then we've got another transaction. We're importing the contract hello world from the account 0x02. And this transaction will create a new capability for the hello asset resource in storage and adds it to the account's public area. Other accounts and scripts can use this capability to create a reference to the private object to be able to access its fields and call its methods. So we import it, we've got the comments, then we've got a transaction, we prepare the account with auth account, then we've got a capability, a hello reference, and a log. 3 things. We've got a capability, a hello reference, and a log. We want to ensure 0x02 is still selected as the transaction signer. Click the send button to send the transaction. We're going to make sure that 0x02 is the transaction signer. We'll send the transaction, and we got a result out that says hello world. Great. Just keep moving. You should see hello world show up in the console again. This is because we created a capability for the hello asset object, stored the capability in public /hello, borrowed a reference from the capability, and used our reference to call the hello method of the object. Capabilities are kind of like pointers in other languages. The /storage/ domain of account storage is private, but users will still want to allow other users to access the functionality of their private objects without having the ability to remove them. In our example, the owner of hello asset might still want to let other people call the hello method. This is what capabilities are for. They represent a link to an object in an account storage that has the type specified when the link is created. Capabilities do not have any meaningful functionality on their own, but every capability has a borrow method which creates a reference to the object that the capability is linked to. This reference is used to read files or call methods on the object they reference as if the owner of the reference had the actual object. Note that this only allows objects access to fields and methods. It does not allow copying, moving, or modifying the original object directly. Let's break down what's happening in this transaction. First, we create a capability that's linked to the private hello asset object inside of storage. So we let capability equal account.link, so we're using the link functionality. Our object is hello world hello asset. Instead of @ we're using ampersand. We don't know what this is for yet. And then we get it from public. We link it to public hello, and then our target is storage /hello. So it looks like we're linking a public resource with our targeted storage private resource. The hello asset object is stored inside of storage /hello, right over here, which only the account owner can access. They want any user in the network to be able to call the hello method, so they make a public capability in public hello. To create a capability, we use the authAccount.link method to create a new capability to an object in storage. The type contained within the quotes is the restricted reference type that the capability represents. the capability says that whoever borrows a reference from this capability can only have access to the fields and methods that are specified by the type inside of the greater than less than. A reference is referred to by the ampersand symbol. Here the capability references the hello asset object, so we specify hello world.hello asset as the type, which gives access to everything in the hello asset object. The first argument to the link function is the path where we want to store the capability, and the target argument is the path to the object in storage that is to be linked to. To borrow a reference to an object from the capability, we use the capability's borrow method. So hello reference equals capability, the force unfurl, the force unwrap dot borrow. Question panic could not borrow a reference to the hello capability. This method creates a reference as the type we specified inside of our quotes, inside of our greater than less than, in the link function. Here we use the force unwrap operator exclamation mark because the capability is optional. If the capability is nil, the transaction will abort. While borrowing the reference, we use optional chaining because the borrowing of the reference could fail. The reference could be nil, and if the targeted storage slot is empty, is already borrowed, or if the requested type exceeds what is allowed by the capability. We panic with the descriptive error message so that the caller can know better what went wrong. The reason we separate this process into capabilities and references is to protect against re-entrancy bugs, where a malicious actor could call into an object multiple times. These bugs have plagued other smart contract languages. Only one reference to an object can exist at a time, so this type of vulnerability isn't possible for objects in storage. Additionally, the owner of an object can effectively revoke capabilities they've created by moving the underlying object or destroying the link with the unlink method. If the referenced object is moved or the link is destroyed, capabilities have been created from that link are invalidated. You can find out more detailed documentation about capabilities in the language reference. So now anyone can call the hello method on your hello asset object by borrowing a reference with your public capability in public/hello. Let's read that again. Now anyone can call the hello method on your hello asset object by borrowing a reference with your public capability in /public/hello. Lastly, we call the hello method with our borrowed reference. Let's take a look at this resource borrowing. So again, we've got a transaction with our auth account, which we're calling account. We then create a capability where we link the object type of hello asset from our storage hello. We link it to a public resource called hello. Once we create that link, we then create the reference where we say capability, conditionally unwrapping that if it exists, because it might not exist, and then we borrow that resource. If it doesn't work, we then use our conditional chaining to panic, which is going to throw in the error, and that's our message. Could not borrow a reference to the hello capability. After we borrow the capability, we then log the borrowed reference's hello function. That's everything in this transaction. That's everything. So we've now created the capabilities and references to stored resource. Next up, we're going to be executing scripts. A script is a very simple transaction type in Cadence that cannot be performed, or that cannot perform any writes to the blockchain and can only read the state of an account. It runs without permissions from any account. To execute a script, you write a function called pub fun main. You click the execute script function to run the script. The result of the script will be printed in the console output. So we will open up script1.cdc, and it should look something like the following. Script. We've got the main function. A script is a special type of Cadence transaction that does not have access to any account storage and cannot modify state. Any state changes that it would do are reverted after execution. Scripts must have the following signature: pub fun main import hello world from 0x02. So we have to import a contract, and we have to declare our function with pub fun main. This right now is sounding very similar to a pure function or a view function inside of Ethereum in Solidity, where it doesn't cost any gas because it's not actually writing anything to the blockchain. It's just reading from the blockchain, or possibly not even reading, and it's just doing work totally unrelated to the blockchain in terms of a pure function. The script fetches the public account object with get account. So we then get account from our account 0x02, and we assign that to hello account. The public account object is available to anyone in the network for every account, but only has access to a small subset of functions that can only read from the public domain in an account. See more about accounts here at the following link. Then it gets the capability that was created in create link. So we get the public capability from the public path of the owner's account. So we assign a variable of hello capability, we load in our hello account, we get the capability from the path public/hello. So we can load in any account, and then we can get any public capability from their public methods. To get a capability that's stored in an account, we use the account.getCapability function. This function is available on auth accounts and on public accounts. It returns a capability at the path that is specified, also with the type that's specified. It does not check if the target exists, but the borrow will fail if the capability is invalid. After that, the script borrows a reference from that capability. So once we have loaded the capability, we then borrow a reference to that capability. Then the script uses the reference to call the hello function and prints the result. Let's execute the script to see if it runs correctly. We're going to click the execute button in the playground, and we should see something like this, where we get hello world and then the result is void. Let's execute. We don't need, unlike these transactions where we need a transaction signer, for a script we don't need a transaction signer. We can execute it. We then get two logs, one where we log hello world, and then the other where we log result of type void. Good work. We've deployed our first smart contract with Cadence and used transactions and scripts to interact with them. Here are a few pointers on certain aspects of the playground if you still need some clarification. Let's go back and read through this function, the script real quick, just to make sure that we've got it all. So we already talked about our header and our definitions and our imports. Let's go into the actual script. So the first thing we do is we declare a variable called hello account, where we get account. It's a built-in function, and then we pass in an account that we want to get. This can be any public account object. After we get that account, we then want to get a public capability from the public path of that owner's account. So we then take hello account, which is this account 0x02, and then we get a capability from it that is of type hello world.hello asset at the path public/hello. We assign that capability to our local variable. After we assign the capability, we then borrow a reference of that capability and assign it to a local variable. If that capability does not exist, we then panic and we print out an error message, could not borrow a reference to the hello capability. We then use the built-in log function to log its arguments in the standard output. Here we're using optional chaining to call the hello method on the hello asset resource that's referenced in the published area of the account. I don't actually see any optional chaining here. I think the optional chaining is happening up here with our panic, but I think if we didn't want to use the panic, what we could do is we could get rid of this conditional panic, and then we can make this conditional. So you can see this doesn't like it because the error is this might not exist. It's got no member, but if I make it conditional, now we're all looking good. And what happens if we execute? We're still looking good. Either way I think works. Let's keep moving. Great work. We deployed it. Now we're moving on from executing our scripts into accounts. So the playground is initialized with a configurable number of default accounts when you open it. In the playground, you can select accounts to edit the contracts that are deployed for them by selecting the tab for that account in the left section of the screen. The contract corresponding to that account will be displayed in the editor, where you can edit and deploy it to the blockchain. Upgrading contracts that are already deployed is very risky, so please be careful. Transactions. Let's quickly just look at accounts. So we've got all these accounts. Very simple. We can deploy a contract to that account. It gets deployed. We can see it. We can go through. We can deploy all these accounts. Hunky-dory. Blah, blah, blah. Boom. We've deployed a bunch of contracts. The only one that we can't deploy a contract to is number 5, because there's no contract available. Transactions. Once a contract's been deployed, we can submit transactions to interact with it. In the transactions selection section on the left side of the screen, you can select different transactions to edit and send. While a transaction is open, you can select one or more accounts to sign a transaction. This is because in Flow, multiple accounts can sign the same transaction, giving the access to their private storage. If multiple accounts are selected as signers, this needs to be reflected in the signature of the transaction to show multiple signers. So for one signer, we would have account 1 in auth accounts. If we are allowed 2 signers, we would do account 1 and account 2, which are both auth account objects. If you want more practice, you can run some of the previous transactions on new accounts to explore some different interactions and potentially some of the error messages. Okay, great work. I know that was a lot. If you're not familiar with Cadence, I'm sure you feel like you just got a fire hose to the face of information. If you're familiar with Solidity or other smart contracts, hopefully some of this feels familiar. But if you didn't catch it all, don't worry. Take it slow, watch this lesson again, go through and do it yourself without me talking to see if it makes more sense to you. If everything did make sense, let's move on to fungible tokens on Flow. So fungible tokens are different from non-fungible tokens, or NFTs. And we'll talk about both of those in the next section of our Flow blockchain developer course. If you have any questions, send us a message, send us a comment, message us on any social media site at VoiceFirstAI. If you're not already subscribed and you're watching this on YouTube, please like and subscribe. Other than that, thank you everyone for joining us. This is Sweets, signing off.